The 9 most frightening theories about the universe. Since humans first appeared on Earth, they have wondered how the planet they live on, and the whole universe around it, came to be. Over time, many ideas have been suggested, starting with some that seemed obvious at the time, like the belief that the Earth was flat. Then came Einstein's theory of general relativity, which completely changed physics and introduced ideas so strange they seemed unbelievable to many people, including experts. How did the universe begin? Why does it look and behave the way it does? Throughout history, dozens of theories have tried to answer these questions, and some are not just unsettling but truly frightening. In this video, we will explore some of the most interesting scientific ideas about the universe, matter, space, and time, including SpaceTime, a complex four-dimensional concept Einstein came up with that mixes space and time and is tough to fully understand. Before we start, please subscribe to our channel and turn on notifications so you don't miss our new videos. 1. The Multiverse Theory. This idea suggests there is a huge multiverse made up of many smaller universes. All of these universes together include everything that exists: matter, space, time, energy, the laws of physics, and information. These different universes are often called parallel universes, alternate universes, or multiple universes, and they all follow the same basic physical laws. The theory isn't new. People have been discussing it for over 2,500 years, ever since ancient Greek philosophers first thought about it. The 6th century BCE philosopher Anaximander suggested the idea of many infinite worlds, though it's not clear if he meant worlds existing one after another or at the same time. Later Greek thinkers like Leucippus, Democritus, Epicurus, and Lucretius were among the first to talk about countless worlds. As science developed, the idea grew and was explored in fields like cosmology, philosophy, physics, astronomy, and mathematics. Some physicists say the multiverse is more a philosophical idea than a scientific theory because it can't be tested or proven wrong. Recently, some scientists have looked for evidence of other universes, but opinions are divided. Some support the idea, while others remain doubtful. Critics argue the multiverse can't be tested or disproved, which are important parts of scientific research, making it a tricky concept. Cosmologists like Max Tegmark and Brian Greene have suggested 4 types of multiverses. Level 1 is a simple extension of our own universe. Level 2 includes universes with different physical laws. Level 3 is based on the many worlds interpretation of quantum mechanics. And Level 4 is the mathematical universe, which is the idea that everything can be explained by a single theory covering all aspects of reality. 2. The simulation theory. This theory says that everything we experience is actually a computer simulation. It might even include conscious minds that either know or don't know they're living inside this simulation. People often mix up simulation theory with virtual reality, but they are different. Virtual reality creates computer-generated scenes that feel real but are still clearly not the same as actual life. A simulated reality, on the other hand, would be almost impossible to tell apart from true reality. This idea has sparked many debates, especially about its philosophical implications. The main supporter of this theory is Swedish philosopher Nick Bostrom, who founded Oxford University's Future of Humanity Institute. In 2003, he wrote a paper suggesting that we might be living as virtual beings inside a computer simulation. Since then, philosophers, physicists, and other experts have discussed the idea. Bostrom imagined an advanced civilization with huge computing power that could easily create simulations filled with conscious beings. Before Bostrom, the idea became well known thanks to the 1999 film, The Matrix. The concept goes back much further, with connections to old philosophical ideas like Plato's allegory of the cave and Zhuangzi's butterfly dream. More recently, entrepreneur Elon Musk has brought attention to the theory, saying in 2016 that the chances we are living in real reality are extremely low, like 1 in billions. William Hohmann, a computational math expert from Caltech, pointed out that if a simulation had unlimited computing power, it would be impossible to detect because it could perfectly recreate reality. But if it's possible to notice, that means the computing power is limited. Some scientists are more critical. For example, German physicist Sabine Hossenfelder called it pseudoscience. And South African cosmologist George Ellis said it's not practical from a technical point of view. Many critics think supporters confuse science fiction with real science, and that casual talks in bars don't make a solid scientific theory. 3. White hole theory. In general relativity, a white hole is a theoretical region in space that acts like the opposite of a black hole. Instead of pulling things in, it pushes everything away. Matter, light, energy, or information can't go into it, and nothing can get inside from the outside. While nothing can escape a black hole, nothing can enter a white hole. Stephen Hawking and other scientists once suggested that the massive black holes we see in space might also create equally massive white holes. For a long time, most scientists saw white holes as unrealistic outcomes of Einstein's equations, the same ones that predict black holes. But more recently, some physicists have started to wonder if white holes and black holes could actually be two sides of the same thing. Think of a white hole as a black hole in reverse. It's like watching a video of a black hole played backward, or like imagining a ball bouncing up instead of falling down. A black hole's boundary is a point of no return. Once you cross it, you're stuck. A white hole's boundary is the opposite. Nothing can get in, no matter how hard you try. In theory, objects could come out of a white hole and enter the universe. But since nothing can go in, what's inside is completely cut off from the rest of the cosmos. That means no event outside can affect it. Some scientists even think the idea of a singularity in the past, something that could affect the universe from before time as we know it, might be even more unsettling. Einstein's general relativity shook the world of physics like an earthquake back in 1915. Says James Bardeen, a retired professor from the University of Washington and an early expert on black holes. His theory changed the way we understand reality, how space and time bend around things like stars and galaxies. It confused a lot of scientists at first. It took 40 years to understand black holes. Only recently have people started looking seriously at white holes, adds Carlo Rovelli, a theoretical physicist in France. Maybe this time, it won't take as long. 4. Superfluid spacetime theory. The superfluid vacuum theory, or SVT, is a scientific idea that suggests the vacuum of space, the empty part of the universe, might actually act like a superfluid, a strange form of matter that flows without any resistance. Back in the 1920s, Albert Einstein and Indian physicist Satyendra Nath Bose explored the behavior of light particles, or photons. Bose came up with rules for when two photons should be considered the same or different, and Einstein applied those ideas to atoms in a gas. They discovered that at extremely cold temperatures, many atoms collapse into the same low-energy state. This collection of atoms is called a Bose-Einstein condensate. In 1995, American scientists Eric Cornell and Carl Wyman managed to cool atoms to just a tiny bit above absolute zero, the coldest temperature possible. They created a Bose-Einstein condensate in the lab, earning them the Nobel Prize in 2001. This strange state of matter is a superfluid. It has no friction and can flow forever without slowing down. Now, some physicists think that space-time itself might be a superfluid. Space-time is the four-dimensional fabric that combines the three dimensions of space with time. According to this theory, space-time isn't just a backdrop where things happen. It's a physical thing itself, kind of like an invisible ocean. Luca Mazzone and Stefano Liberati have proposed that, just as water is made of molecules, space-time might be made of tiny particles we haven't been able to detect yet. In this view, space-time behaves like a superfluid with no viscosity. And unlike normal liquids, which spin as a whole when stirred, superfluid space-time would break into swirling patterns, vortices, that could have helped shape galaxies when the universe was forming. 5. The cyclic universe theory. This theory about how the universe began and how it works was developed by physicists Neil Turok from South Africa and Paul Steinhardt from the United States. The idea is based on an ancient Greek concept called ekpyrosis, which means a cosmic fire or a transformation through fire. In ancient philosophy, this fire represented the part of a never-ending cycle where the universe is destroyed and then reborn. The cyclic universe theory suggests that instead of expanding from a single point like in the Big Bang model, our universe came from a collision between two giant, invisible structures called brains. These brains come from M-theory, which tries to bring together all the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. According to this idea, the universe goes through endless cycles of fiery creation, cooling down, and then starting over again. This model offers a different answer to one of the biggest questions in cosmology. What came before the Big Bang? The ekpyrotic theory says the Big Bang wasn't the beginning, but more like a bounce, where a shrinking universe flipped into the expanding one we live in now. Everything that shaped our universe may have happened before that bounce, and this process might repeat again and again. Interestingly, many modern versions of the cyclic model use the same basic physics as the inflationary Big Bang theory. The cyclic model also predicts that the universe should look mostly the same in every direction, with small variations in temperature, cold and hot spots, which matches what scientists have seen in the cosmic microwave background, CMB, the afterglow of the early universe. Supporters of this model argue that the CMB could also be evidence of a big bounce, not just the Big Bang. One major benefit of the cyclic model is that it avoids the idea of a multiverse. In inflation-based theories, quantum effects can create many different universes, making it hard to explain why ours looks so uniform. Cyclic models don't have this problem. However, critics point out that the cyclic theory depends on ideas from string theory, like the idea that particles are actually tiny, vibrating strings. Not all scientists agree with this. Another issue is that no one really knows what would happen when two brains collide, which is a key part of the theory. 6. The Big Bang theory. More than 90 years after Belgian scientist and priest Georges Lemaitre introduced it, the Big Bang theory is still the most widely accepted explanation for how the universe began. It's based on two major discoveries. The universe is expanding, and it's filled with faint microwave radiation from its early days. The theory says that the universe started from a very small, extremely hot and dense point that eventually expanded and gave rise to everything: space, time, and matter. Lemaitre first called this starting point the primeval atom. The nickname Big Bang was actually meant as a joke by British astrophysicist Fred Hoyle during a radio broadcast in 1949, but it stuck. According to the standard version of this theory, the Big Bang happened about 13.8 billion years ago. The theory doesn't try to explain what caused the Big Bang, only what happened afterward. For the first few 100,000 years, the universe expanded and cooled down until atoms could form and light could travel freely. As the universe kept growing, particles came together to form atoms, which then formed stars, planets, and galaxies thanks to gravity. This process gave us the structure of the universe we see today. Lemaitre's idea that an expanding universe must have started from a single point gained strong support when Edwin Hubble found in 1929 that galaxies are moving away from each other. This discovery confirmed that the universe is expanding. Over time, the Big Bang theory beat out Hoyle's alternative, the steady-state theory. Ironically, even though Hoyle doubted the Big Bang, he helped name it. 7. The steady-state theory. After Edwin Hubble discovered that the universe is expanding, some scientists who were skeptical of the Big Bang came up with a different idea called the steady-state theory. According to this theory, as the universe expands and things spread out, new matter is constantly created to keep the overall density the same. The theory is based on the perfect cosmological principle, which says the universe should always look the same to everyone, no matter where or when they are observing it. So, in the steady-state view, the universe doesn't really change over time. Its basic features always stay the same. The idea first appeared in the 1930s, suggested by British scientist James Jeans. In 1948, Fred Hoyle, along with Thomas Gold and Hermann Bondi, developed it further. They realized that a universe that never changes wouldn't work with Einstein's general theory of relativity, especially since Hubble had already shown that the universe is expanding. So they updated the theory to accept expansion, but still argued that the universe keeps the same overall density because new matter is constantly popping into existence. Interestingly, even Albert Einstein briefly considered a similar idea in 1931, but he quickly dropped it. By the late 1960s, problems with the steady-state theory became clear. Scientists noticed that quasars, extremely bright and distant objects, only appeared far away in the universe, meaning they existed a long time ago, but not nearby, which meant they weren't still forming. That was a big blow to the theory. The final nail in the coffin came in 1965 with the discovery of the cosmic microwave background, faint radiation left over from the early universe. According to the steady-state theory, there shouldn't be any such background because the universe had no beginning. To explain it, the theory would have needed a complicated and unlikely explanation involving special particles absorbing radiation, something most scientists didn't buy. Still, the theory isn't completely forgotten. It has a few supporters, like Indian astrophysicist Jayant Narlikar, who worked with Hoyle to create the Hoyle-Narlikar theory, which tried to connect Einstein's ideas with Mach's principle, the idea that the inertia of an object depends on the mass of the universe around it. 8. The Goldilocks planet theory. The term Goldilocks planet is used to describe an exoplanet, a planet outside our solar system, that lies in the just right zone around its star, where it's not too hot and not too cold for life to exist. These planets are often similar to Earth in size or other features. The name comes from the fairy tale Goldilocks and the Three Bears, where Goldilocks always picks the option that's in the middle, not too extreme in either direction. Goldilocks planets are especially interesting to scientists who are searching for alien life or thinking about where humans could possibly live in the future. Finding these kinds of planets helps scientists improve the Drake equation, a formula used to estimate how many intelligent civilizations might exist in the universe. One part of that equation depends on how many planets in a star system could support life. If there aren't many Goldilocks planets, that supports the rare Earth idea, which says Earth is special and life here happened because of very rare circumstances. But if there are lots of them, it supports the idea that Earth is just one of many similar planets. NASA's Kepler mission, launched in 2009, focused heavily on finding Goldilocks planets. Before it ended in 2018 when it ran out of fuel, Kepler gave us some amazing numbers. It estimated that there are more than 40 billion potentially habitable planets in our galaxy, the Milky Way. About 11 billion of those may be orbiting stars similar to our Sun. That means the closest Earth-like planet could be just 12 light-years away from us. 9. The sterile neutrino theory. Neutrinos, whose name means little neutral one, are tiny subatomic particles with no electric charge. They were first discovered in 1956, and ever since, scientists have been debating whether they have any mass at all. Around the early 2000s, experiments in Canada and Japan confirmed that neutrinos do have mass, although it's incredibly small, about 1/1,000,000th the mass of a hydrogen atom. One interesting idea is the existence of sterile neutrinos. These would be a new type of neutrino that doesn't interact with matter through 3 of the 4 known fundamental forces: electromagnetism, the strong nuclear force, or the weak nuclear force. The only force they respond to is gravity. That's why they're called sterile, because they don't interact in the usual ways. Unlike regular neutrinos, which do take part in the weak nuclear force, regular neutrinos are also left-handed, while sterile neutrinos are thought to be right-handed. Scientists are especially interested in sterile neutrinos because they could help explain some of the universe's biggest mysteries, like dark matter. Dark matter is a kind of invisible substance that makes up most of the matter in the universe. We can't see it or detect it directly because it doesn't interact with light or other forms of radiation, but we know it's there because of its gravitational effects. Sterile neutrinos might also play a role in explaining how matter first formed after the Big Bang, a process called baryogenesis, or be part of a still hypothetical form of energy known as dark electromagnetism, which could also relate to dark matter. In 2018, scientists working on an experiment in the US called Mini-Boon reported some signals that looked like they might be from sterile neutrinos. This caused a lot of excitement, but as of 3 years later, there's still no solid proof that these particles exist. And if some of this stuff, like general relativity, seems confusing, don't worry. You're not alone. The famous Danish physicist Niels Bohr, who won the Nobel Prize in 1922 and was a close friend of Einstein, was once asked by a student to explain general relativity in simple terms. He reportedly replied, "Keep searching. And if you find someone who can explain it clearly, have them explain it to me too." That's how complex and mind-bending some of these ideas can be. We hope you enjoyed this video. If you have any thoughts or questions, feel free to drop them in the comments. Like and share this video with your friends and family so they can learn about the 9 most mind-blowing theories about our universe. And if you're new to this channel, hit the subscribe button. Remember, those who don't understand the past are likely to repeat it. This video is a reminder that what we experience as everyday reality is just a tiny part of a much deeper and stranger universe. Science brings us fascinating theories about multiverses, simulations, white holes, and more. But they're not just academic ideas. They challenge us to think about who we are and what our place is in this vast, mysterious cosmos. Just as science explores the big questions of the universe, spirituality encourages us to look beyond the surface of things, question what we think we know, and find deeper meaning. These scientific theories might sound strange, but they echo some of the same questions people have been asking for thousands of years. Why are we here? What is reality? Who are we, really? By exploring these ideas, we're not just learning about space. We're also learning about ourselves. These discoveries remind us that reality may be far more complex and amazing than we realize. And that can inspire us to stay curious, to stay open, and to keep asking questions. Because at the end of the day, the search for truth, whether scientific or spiritual, is one of the most meaningful journeys we can take. This video is just one small step on that path, showing us that the universe is full of wonders we've only just begun to understand.